In its final moments, the Titanic did something that should have made finding its wreckage simple. It broadcast its exact coordinates to the world. Those numbers were effective in the immediate aftermath. The nearby RMS Carpathia used them to navigate directly to the site, successfully pulling every living survivor from the freezing water. If the rescue ships knew exactly where the survivors were floating on the surface, locating the wreck directly below them should have been a straightforward dive. Instead, it triggered a mystery that lasted over 7 decades. The barrier was the vertical drop. The ship lay 2.5 miles down, a depth unreachable by human divers in 1912. Early recovery ideas were desperate, ranging from using giant magnets to dropping dynamite, just to blast bodies loose from the wreckage. The sheer gap between knowing a ship's surface location and possessing the technology to reach it created a complete standstill. It would take 2 world wars and the invention of advanced sonar before anyone could even attempt a serious search. When explorers finally did return decades later, they hit an immediate mathematical roadblock. The supposedly perfect coordinates broadcast by the Titanic were wrong. As the ship traveled, the first officer failed to account for a time change in his calculations. Combined with 2 hours of sinking time and ocean currents pushing the vessel off course, the actual drop zone shifted miles away. This map shows how those physical errors compounded. The original pinpoint location grew into a massive 1,500 square mile search box, a completely different reality for anyone trying to comb the bottom. Inside that grid is total darkness. Trying to find a single static object down there by slowly checking point after point is a statistical longshot. The search wasn't just limited by the extreme depth. The math of the search area was broken from the very first day. The first attempts to solve this problem relied on brute force. In 1953, Riston Beasley dropped explosives over the reported location, hoping to map the ocean floor using the crude echoes of the blasts. It yielded no results. Decades later, Texas oil tycoon Jack Grimm tried a different kind of brute force: wealth. He poured hundreds of thousands of dollars into his expeditions, but he lacked scientific rigor. Grimm was an eccentric who had previously searched for Bigfoot. At one point, he brought a monkey on board his ship, claiming the animal could point at a map to locate the Titanic. Even when the scientists on his crew persuaded him to leave the monkey behind, his team pressed on with broken equipment, unable to verify if the shapes they scanned were actually metal. These teams used a scanning methodology known as mowing the lawn. They towed a sonar probe back and forth in tight overlapping lines, meticulously scanning the seabed for a ship-shaped silhouette. This hyper-focused protocol bred false positives. When staring at narrow strips of the ocean floor, natural rock formations often look like man-made propellers, tricking teams into thinking they had found a piece of the ship. Financial resources and repetitive scanning were useless because the underlying search methodology ignored the deceptive scale of the ocean floor. While Grimm was busy with his expeditions, a marine geologist named Robert Ballard was watching from the sidelines. Ballard lacked a tycoon's fortune, but he had a unique advantage: access to the U.S. Navy. The Navy struck a deal. They would fund Ballard's advanced deep-sea equipment, but only if he used it to map the wreck sites of 2 destroyed nuclear submarines first. This provided the resources to develop Argo, a deep-towed sled. Unlike previous sonar systems, Argo provided real-time video of the ocean floor, allowing for immediate visual identification. While mapping the nuclear subs, Ballard noticed something about how objects behave under extreme pressure. As heavy warships sink, they implode, creating a debris field as they descend. He identified this as a comet trail. While the heaviest pieces sink straight down, ocean currents carry lighter materials away, creating a massive underwater debris field that spans for miles. Ballard's strategy shifted the focus away from the ship itself. While previous explorers hunted for a tiny needle in a massive haystack, his work with the nuclear subs showed him a much larger target: the debris field created by the physics of the descent. In 1985, Ballard finally had his chance to search for the Titanic, but the deadline was tight. He had only 12 days to use the Navy's equipment before he was forced to return home. With limited time, Ballard deployed a radical strategy. Instead of tight lines, he spaced his search incredibly far apart. He might miss the hull entirely, but because currents stretched the debris into a mile-long trail, this wide grid was highly likely to intersect the wreckage. the pressure on the crew was immense. They operated in shifts around the clock, staring at blurry video feeds of the ocean floor, waiting for any sign of man-made debris to break the natural landscape. By relying on these physical rules, Ballard transformed a major disadvantage, limited time, into a calculated search designed to maximize the chances of intersection. Late one night, the blurry rocks on the monitors began to take on more specific shapes. These weren't natural features of the seabed. The crew finally spotted one of the Titanic's massive boilers. Ballard's theory was proven. They had successfully intersected the debris field. By following the comet trail of debris directly to its source, the team located the ultimate prize, the massive, intact bow of the Titanic. The discovery revealed a striking irony. The wreck was sitting just 3,300 feet from where a previous expedition had passed by without seeing a thing. Ballard and his crew honored the victims with a moment of silence, a solemn respect that stood in contrast to the media spectacles and artifact recovery attempts that would follow in later years. Finding the wreck didn't require searching harder. It required observing the physical rules of the environment and changing the parameters of the search to match them.